Welcome everybody, both online. Hi, we have our usual UPAC colloquium. This time we have our speaker, Marco Forgione from the University of Milan Statale. And we, as usual, we have 45 minutes of talk, and then we have discussion around 45 minutes. Yeah. So this time we have talk about Hubble constant, robustness issue.
Thank you. Sorry. I'll time myself so that I get an understanding of like how much time that I have.
Yeah, but don't worry.
I'll start like a stopwatch or sort. Okay. So thank you for having me here. Thank you for the introduction. As you were saying, my name is Marco Forgione. I'm a postdoc at the Cosmos project at the University of Milan. And well, the idea for today is to discuss a little bit about Hubble constant and robustness, which is the presentation. But this is basically something that I didn't present this whole presentation already, but I did present like something of a much condensed version in Milan at the last Philosophy of Cosmology conference. And basically had an idea there. The original idea when I started working on this was, well, I want to use a philosophical tool to analyze the philosophical tool, robustness analysis, to analyze the so-called Hubble tension or H0 tension. I will explain these terms in a second. And so the H0 tension, basically, the Hubble parameter, Hubble constant, is a parameter that expresses the rate of expansion of the universe. And the problem, basically, which is a well-known problem in cosmology, is that we have different independent methods to calculate the Hubble constant. And these independent methods, which are, again, calculate the same object, the same thing, are giving different results. So that's puzzling. Why is that the case? That should happen. And so my original idea when I started working on this was, well, I want to investigate whether methods for calculating and measuring H0 are robust or not. Basically, the idea was, well, I take a definition of robustness analysis, and then basically I run it against these different independent methods to calculate H0. And then the question would be, does the H0 tension suggest that the solution to the tension is new physics? Well, the original idea was to run an argument for which, well, I think the problem with the H0 tension, like the resolution to the H0 tension, will probably be in our cosmological model, probably because we need new physics that is yet unaccounted for. Well, this was the original idea, the idea that on top argued for, even right before the conference in Milan. And then, well, after I started looking into the matter a little more deeply, I don't think it's possible, not at least in the terms I just explained. So I think the actual thing that we'll need to do, or the thing that we'll discuss today is, well, if you want to use robustness analysis, and be aware this is not mandatory, it's just, well, I want to see if I can use robustness analysis to investigate the Hubble tension. But if you want to use robustness analysis, then we need some better notion of robustness analysis. And in this whole presentation, basically, I will show you why that's the case and a little bit of what type of work is needed if we actually decide to go on that route. So let's talk about the Hubble constant a little bit. I think you probably all know this, but it's still nice to like repeat things. Sorry. So let's start with Friedmann equations. They're among the most important equations in modern cosmology. They describe the expansion of the universe under the assumption of the cosmological principle, which is homogeneity and isotropy. We'll talk louder than the drill. They express the expansion rate based on energy content and curvature, and they express the acceleration expansion based on pressure, fluid, and dark matter. And so I found like an interesting and easy derivation of Friedmann equations. It's obviously a simplified derivation from a textbook in 2015, where we just use gravitational potential, the kinetic energy of a test particle, energy conservation, relativistic corrections, and then Newton's shell theorem. And I want to go through these real quick just to have an idea of what we are talking about in terms of Hubble's constant. So imagine we are an observer in a uniform expanding medium. Here, the gray area that you see on the slide, and which is basically a representation of the universe. Because the universe looks the same from anywhere, cosmological principle, then we can pick whatever we want as its center. And then we have Newton's Shaw theorem, for which the gravitational field inside a spherical homogeneous object, in this case, our universe, or in the slide, basically the area, at a distance r from its center, is the same as if the total mass was centered at the object's center. So basically, the idea is simply that the mass m over there feels the gravitational field, or the gravitational potential, from as if the entirety of the mass was centered on the central point. And basically, by doing some equation and calculations, basically we want to calculate, the how r basically evolves in time, which is the expansion of the universe, or the uniform expanding medium in this case. And basically we switch to co-moving coordinates, and what we obtain is a scale factor for this gray area, or in this case, the scale factor of the universe, which measures how physical separation grows in time. And from there, we can obtain basically Friedmann's equations. How is this related to Hubble's constant? Well, basically, if you think about Hubble's law, for which galaxies move away from us at speeds proportional to their distance, basically the term h in Hubble's law, which is Hubble constant, can be proven to be equivalent to the term here in Friedmann's equations. And so basically, we are using Hubble's constant, or in this case, basically, it's the rate of expansion of the universe, or in the case we saw before, the rate of expansion of the distance from the mass to the central point. Something popped up on the.
Sorry, yeah, someone's saying they're not seeing the screen, and now they are, I think. Can someone online confirm that you're seeing the screen? Yeah. Okay, great.
Okay. So we were here. So again, basically, the idea is we want to now measure this parameter, Hubble constant, which again expresses the rate of expansion of the universe. And to do so, it should be fairly easy, right? We just look at the galaxy, see how the galaxy basically moves away from us. We measure the velocity, and then basically we're like, okay, so based on how far away it gets from us in a certain amount of time, then we have the expansion rate of the universe. Easy peasy. Well, not exactly, because galaxies are surrounded by other cosmological objects, such as galaxies. And basically, we cannot just look at a nearby object, cosmological object, and just calculate the rate of expansion of that, the rate of distancing of that object, because there are factors such as gravitational effects that would impact the rate of expansion of the universe, or at least our calculation of the rate of expansion of the universe. So basically what we need to do is we need to look for cosmological objects that are far away into the universe and distanced enough from each other that basically the gravitational effect of nearby objects is not strong enough to affect basically the actual velocity due to the expansion rate of the universe. So we need to look at objects that are in the Hubble flow, where the Hubble velocity is much larger than the peculiar velocity. We'll do so by calibrating distances on luminosity and by calculating measures to nearby objects and then farther away objects in a method called the distance ladder method. But before moving to that, I wanted to look at some of the history of the Hubble constant. At the history of the Hubble constant, basically, Hubble 1925 established a relationship between redshift and galaxy distance, and he estimated h naught to be around 500 kilometers per second per megaparsec, which is a big number, especially because according to that number, the universe would be about 2 billion years old, which is kind of incompatible with our observations. And so clearly there was something missing there, or the precision of the measurements was not enough. So in the 50s, Stevenson, Milan, and Sandage, 1956, published a paper of work where they calculated h naught to be around 180 kilometers per second per megaparsec. And basically they used spectroscopic data from past years, from 1935 to 1955, featuring more than 800 redshift of galaxies. Then until the 70s, basically the main work was done by Berg, who basically summarized the methods for calculating H0, and not many new instances of such calculations came to be because, well, there were technological limitations. Sorry, that was a weird word. Technological limitations basically made it really hard to calculate distances of cosmological objects precisely enough so that we could have like a better estimate of H0. Notably, in 1965, we had the detection of the CMB, which basically validated or gave more reasons to believe in the Big Bang model. And so scientists started to assume that, well, the Big Bang model, which was just validated because of the CMB, should give like a estimate of the H0 that was comparable or compatible with any measurement of H0 using other methods. Why is that so? Well, because we want to say that our theory about the origin of the universe is compatible with basically its evolution. Like they should not discord too much because otherwise it won't make much sense. Then we have a bit of an evolution of the measurement of H0 in the 70s and in the 80s, where basically we had the development of two main camps, two main blocks. Low value H0 being equal to 50 to 57, and high values of H0 being between 90 and 110, still kilometers per second per parsec. For example, in 1977, we have the Tully-Fisher relation, which is a correlation between absolute luminosity of spiral galaxies and their rotation rate. And through that, scientists calculated H0 to be in the ballpark of 75 to 85. Aronson and others in the 80s calculated H0 to be between 90 and 95. And then they used methods such as surface brightness fluctuations, calculated H0 to be 77 and between 77 and 88. So like about all these numbers and people, what I want to emphasize is that in the 70s and the 80s, we have basically a division between possible values for H0, a high value for H0 between 90 and 110, and low value between 50 and 57. This distinction basically got solidified even later with the Hubble Space Telescope, the measurement and observations from the Hubble Space Telescope, and then with the Planck project, where basically H0 was solidified to be about 72 kilometers per second per megaparsec using HST observations and the distance ladder method. And then H0 was calculated to be around 67 by Planck using, for the most part, CMB observations and later on values. So this is basically this last point, 72 and 67, is pretty much the current point of the tension where we have these two values, early universe against late universe. And this is the problem that I was emphasizing earlier. Basically, we have two different methods to calculate the same object, the same parameter, sorry, and we don't know why we're getting different results, even though these two methods should give clearly the same result. They're measuring the same thing. So in this presentation, so like as I again mentioned here, there are two methods for calculating H0. In this presentation, I'll focus for the most part on data from observation data, for example, from HST, and then I'll say something about James Webb Space Telescope, but I will, for the most part, focus on the distance ladder method, so the calculation of H0 based on optical observations and measurement from space telescopes. So, what is the cosmic distance ladder method? Well, it's a method to calculate distances that are too far away for our instruments. So as I was saying, to calculate H0, we need to look at cosmological objects that are very, very far away. And we cannot just point our telescopes onto those objects and just measure the distance. It's not possible. There is a technological limitation there. So what we do, we use a cosmic distance ladder, which is constituted by of 3 rungs. This is a bit of a simplification, but gives all the idea of how it works. We have a 0-point calibration, which is basically optical observations of Milky Way or Large Magellanic Cloud. we use geometric parallaxes, so basically trigonometry, to measure distances and then intrinsic brightness of certain objects. Basically, we're looking at the distances of nearby objects, we calculate the intrinsic brightness, and that should be easy enough. Then we use those distances and those brightness to look for similar objects in farther away galaxies, and this would be the second rung. For example, we applied to Cepheids in host galaxies to determine distance of those galaxies that are farther away than those cosmological objects that were measured in the first rung. Then, from the second rung, then we measure objects that are even farther away, for example, by using supernovae type 1a, and then we measure basically the distance to galaxies that are in the Hubble flow, and through that, with Hubble's law, we calculate age. No, basically. So I have a few measures here. For example, this is from like a conference in 2019 held in Santa Barbara, California, where basically some new methods were presented to calculate H naught. For example, we have the SHOES collaboration, which is led by Adam Rees, has the purpose of refining measures of H naught using Cepheids and supernovae type 1a. Cepheids, I mentioned that even earlier, they are variable stars. They have a pulsating period luminosity relation that makes them very good for standard candles, and then they are very good for calculating the distance to nearby galaxies. Then we have supernovae type 1a. They have a predictable luminosity. We know the physics behind them, and they're very good for calculating distance to far away galaxies. Another type of standard candle is Mira stars, which are variable stars, kind of complementary to Cepheids. They have a long period pulsation. They are late stage stars, and they're bright in the infrared spectrum. We have other independent methods. These are not these are independent from the distance ladder, so there are different methods to calculate H naught that were still presented at these conferences. Santa Barbara, for example, Holy Cow makes use of gravitational lensing, and basically it's a system based on time delay cosmography, based on time delay of multiple images from dense quasars. Then we have Megamazel project, which measures the brightness of sources of microwave radiation. We have the surface brightness fluctuations. We use variations of brightness of galaxies due to the variations of the star distribution. I won't focus on these methods since I want to focus on the distance ladder method first, but this is just to show you that there are other methods to calculate H naught that are not necessarily dependent on the distance ladder or much related to the distance ladder. So to reiterate the problem, the H naught tension is the discrepancy between H naught measures. In this case, I'll focus on local late universe and early new universe. You can see from the picture where basically most of the values are around 72 and 75. And we have, on the other hand, on the top left of the picture, we have true values that are calculated using cosmological model dependent methods. And there are values that are, let's say, around 67.4 and 67.5, I think. I can read that. Okay. So, which is a number that is significantly different than the numbers calculated by the other methods. So, now that we've set the ground, so we know what the Hubble tension is, we kind of know a little bit about the Hubble constant and what the problem is in general. The original idea that I was telling you about was, well, how about we use robustness analysis, which is a non-empirical method that I'm going to define in a second, to investigate this so-called Hubble tension problem. The idea was, well, I use robustness analysis to run, to investigate whether the distance ladder method to measure H naught is robust, and to determine whether the method based on CMB, BAO, and understand cosmological model is robust, and then I'll compare the two. So, as I was saying, the idea will fail at a certain point, and I'll show you why. First of all, let us discuss robustness analysis. So it's a philosophical tool implemented by Levins and then discussed by Winsat and Ozak and Sobert, Weisberg, Soler, and many others. So it's a philosophical tool that has been fairly widely discussed in the philosophical literature. To be honest, I feel like one of the best and perhaps more precise definitions can be found now in computer simulations and artificial intelligence, mainly because computer scientists use robustness analysis to investigate whether results from a given machine learning model are robust based on changing values in the data inputs in the initial data set. But the general idea for robustness analysis is that independent derivations of the same conclusion strengthen that conclusion. So yeah, independent derivations, they give a similar conclusion, then the fact that multiple derivations give rise to the same conclusion allows us to say that that conclusion is more likely. Or we can increase our beliefs in that conclusion. So here's the problem though. Robustness analysis, as the general idea is fairly clear, but also the specific definitions are quite diverse, and philosophers have used robustness analysis for different purposes, different scopes, and with very different definitions. So I think there is a form of conceptual disunity in the use of robustness analysis in philosophy, and I just want to give you a few examples. So for example, sorry for the repetition, for example, Levins in 1966 discusses robustness analysis in terms of helping with the dependency of models' results from core and simplified assumptions. So basically, he wants to verify, in a sense, causal powers within a certain model and the causal dependency in general of the results from the assumptions of the model. So we're using robustness analysis within a specific model, but Levins does not really specify what he means by core assumptions, or he does not make a distinction between core assumptions and non-core assumptions. One thing that I think he was definitely right about is that robustness is not a feature of the world, in the sense that there is not something like robustness of data or theories out there in the physics world. It's a matter of epistemology, mainly due to the complexity of our systems. And in this sense, I think it will depend. The use we make it depends on the theory that is under investigation. Then we have, for example, Wimsatt, who suggested a different use of robustness analysis. For example, he talks about robustness analysis in terms of redundancy in scientific theory. He basically picks Feynman's distinction between Babylonian view of scientific theories and Galilean view of scientific theories, where the Galilean view is a set of axioms, basically, and very clear axioms, and from those axioms we derive every single possible conclusion for a given scientific theory, or all the propositions that are in the field of that scientific theory. Babylonian view, on the other hand, is a view for which, instead of having one single way of deriving a given conclusion, we have multiple methods for deriving that same conclusion. It's a much more messier view in a sense, because we don't have a clear set of axioms. We just have like many more axioms that provide redundancies. And by providing redundancies, basically, we the good side is, well, at least according to Feynman, is that if one of the propositions hides a contradiction or implies a contradiction, then that would not make the whole theory collapse, because there are indeed redundancies given by the different assumptions and by the different derivation paths. And so I quote here, robustness provides the best explanation for this phenomenon. Whenever there is an inconsistency or a paradox, it is only one of the independent supports that gets removed, but robustness guarantees that there are other supports that can sustain the theory. So Wimsatt discusses robustness analysis in this case as basically a protection system or a redundancy system within a given scientific theory. So not a model scientific theory. Then we have Woodward, who provided like a taxonomy for varieties of robustness analysis. He discussed inferential, derivational, measurement, and causal. For example, inferential robustness says that given many propositions support a given conclusion, then we have strong reasons to believe that we have strong beliefs to believe in the conclusion, even without knowing which proposition is correct. Sorry. We have derivational robustness, which amount to an insensitivity to parameters change. This is interesting, for example, because consider, for example, Newtonian mechanics, which is theory in a sense that is parameter sensitive. if we change r squared to r cubed, we get fairly different physics, clearly, and very different consequences. Are we going to say that Newtonian mechanics is not robust because of these parameter sensitivity? I don't think so. So again, we need derivational robustness to be tailored to the purpose that it's meant to cover. So in the case of Newtonian mechanics, there must be a difference in terms of like R being like a fundamental parameter in the theory against maybe other parameters where it is actually possible to change them and look at whether the results will be different. Then we have measurement robustness, where we have the measure, where basically we just we measure the same parameter or the same object by changing the measurement methods, and then causal robustness, which is very similar to Levin's original view, for which basically we have we want to check basically the causal dependencies of results from given assumptions. Some other definitions are provided by Odenbach. Robustness analysis allows to discharge idealizations by showing how a model can make similar predictions by including more realistic assumptions. This basically is another version of Levin's robustness, but instead of basically changing parameters the way we want, we just basically try to de-idealize those assumptions. We have Weisberg, who, for example, discussed robustness analysis with respect to the logical Volterra model for predators and prey, and he changed small quantities and small variables in the initial equations by adding, for example, conditions such as in infinite population or finite population, or, for example, limited resources or unlimited resources, and verified basically whether the results were the same or similar, what he called basically robustness theorem. And then Forber in 2007 discussed robustness analysis in terms of reducing the space of possibilities before empirical testing could take place. This is similar to, I think, a recent paper written by Antonio on that matter. And I think basically his claim was that we can use robustness analysis to verify, to investigate alternative possibilities for dark matter, but robustness analysis can only tell us about a limited space of possibilities, can help us reduce the space of possibilities rather than verifying directly one or another model. So why did I discuss all these different definitions? Well, this is just to tell you that there are many definitions for robustness analysis. There are different methods, different applications, and they involve different scopes. Some involve theories, some involve different models, some involve presupposition, assumptions within a single model, and so a conceptual disunity. So for our case, basically, for the case of H0, I think we'll keep the general idea for which independent derivations of the same conclusion strengthen that conclusion and apply to H0. This means that independent derivations of the same value for H0 constitute a justification for that value. So I want to run this basically, I want to use this definition of robustness analysis to investigate H0 and H0 tension and see what we can get out of it. The question will be then, does the H0 tension imply and suggest a crisis of our cosmological model, or are there unknown systematics that can explain that tension? In other words, if we use robustness analysis, can we say something about whether the problem, that the resolution of the tension is to be solved into the distance ladder method or into our cosmological model? So, is the lambda CDM model guilty? So basically, this is the original idea that I had when I started working on this project. Well, it seemed to me that, well, since we have like distance ladder method, which uses basically well-known physics or well-known physics, well, it seems kind of legitimate to say that then the problem is in the cosmological model. And my idea was precisely to run that argument by using robustness analysis. So then the measurements for H0 using Bow method or CMB or observations of the CMB, it's fairly easy to say how they are dependent on the cosmological model. And my argument was pretty much this. Well, this is at least before the conference in Milan. Well, we have the distance ladder method, right? Which is based on distance measures using telescopes and the distance ladder method, and basically like just data analysis and systematic, like accounting for systematic errors and statistics. So that physics, that part of the physics is fairly well covered. We know what's going on there. Then on the other side, we have measurements of H0 based on a cosmological model, because, well, measurements using BAO and CMB, they both rely on our cosmological model. And what about our cosmological model? Well, it is very precise and helps us calculate the number of observations, but it's also true that it presupposes dark matter. And we do have evidences for dark matter. For example, and I here mention a paper published by Richard Dawit. We have that, we have cosmic web large structures. We have BAO amplitude that is too high to be from baryonic matter only. We have baryonic matter alone that does not justify flat geometry and other reasons. So we do have reasons to believe that there is something out there that we call it dark matter, but it's also true that we don't know exactly how it behaves. Matter of fact, we have models and there are studies that try to, for example, reduce the space of possible models for dark matter, as I mentioned earlier, or that they investigate which of such models is more likely to be. And so we have a theory, a cosmological, not theory, sorry, we have a cosmological model that has a big black box in it. And this big black box is basically dark matter. So it seems legitimate to say, well, on the one hand, we have very well verified physics, just observations done by using, for example, trigonometry, which is fairly well understood. And on the other hand, we have measurements of H0 based on a model that clearly has something more again, or that we need to like, it's not entirely complete, or at least there is a black box inside that model that we don't know how to account for exactly. And so it seems too legitimate to conclude that the problem of H0 tension is indeed in the cosmological model, right? Sounds reasonable, at least. Well, in order to make that argument, one needs to verify, at least, that the distance ladder method to calculate H0 is indeed robust. Or at least this is because one wants to be extra careful. So before saying lambda CDM model is guilty for not calculating H0 properly, we just want to say, at least want to verify that the other method, the distance ladder method, is indeed robust enough. And so that's what I set on doing. And first problem, 2021, Wendy Friedman calculates H0 to be around 69 kilometers per second per megaparsec by using a different standard candle, DRGB stars. Which, and 69 is basically a number that sits right in between distance ladder method and the lambda CTM based methods to calculate H0, which then it's not enough to say that, well, my initial argument, well, the culprit is lambda CTM model. It's not enough to discuss that argument, but it's enough to say, well, there's an anomaly there that needs to be accounted for. So I looked into some more papers, and well, you find that, well, different calibrations for TRGB stars indeed lead to different results, which might mitigate these initial measurement from Friedman. So for example, RIS in 2022 published like a new standardized TRGB stars measurement for H0, calculating H0 to be equal 71.5, plus statistics, plus systematics, but they were fairly low. So it would kind of give a better, it would kind of give me hope that my argument to say lambda CDM model is guilty was indeed like a plausible argument. Also, Ozark variabilities, which are small pulsations of TRGBs, were accounted in the measurement for H0. And for example, in 2023, Anderson and collaborators calculated H0 to be 71.8, which is again a number closer to the standard, to the distance ladder method rather than the CDM. So hope for the argument that I was trying to make. Well, in 2023, we also have some data from James Webb Space Telescope. For example, recent collaborators replicate the distance ladder method calculation, the distance ladder calculation of H0 using Cepheid, using James Webb Space Telescope data instead of HST. And they conclude that no new systematics from distance ladder are present, at least by using Cepheid as a standard candle. And here I quote, of some potential concern, at red wavelengths, red giant and bright asymptotic giant branch stars can impact the photometry of the Cepheids. Importantly, with 4 times better resolution than HST at these near infrared wavelengths, crowding effects are decreased by more than an order of magnitude in flux using JWST. The conclusion in their paper is indeed that there are no further systematics, there should not be further systematics in at least the calculation of H0 based on Cepheid standard candles. Good, seems like promising. But then this happens, which is right before the conference in Milan, where basically Wendy Friedman also publishes an analysis, a data analysis, a calculation of the H0 using JWST data. And she calculates, well, her and her collaborators, they calculate basically the same value for H0 using Cepheids as Adam Rees, but they still calculate H0 to be equal to 69 and 67 using different standard candles, mainly TRGBs and JGBs. And so the problem of these outliers values is still there. And so my argument, which was based on the premise that the measurement of H0 using the distance ladder method is definitely robust, therefore the problem must be in the lambda CDM model, kind of starts to crumble, right? Because it seems like the calculations for H0 using distance ladder are not as robust. And indeed, if we look, for example, here, which is like on the table, we have the calculation of distances for TRGBs, Cepheids, and JGBs with respect to the same host galaxies or with respect to the same host galaxy. We see that basically we have TRGBs and JGBs values being much more similar than the values for Cepheids, for the distance with Cepheids. And so here's an issue. It seems there is a second tension, a tension within the tension, not only a tension between H0 for lambda CDM model and distance ladder, but there is also another tension within the distance ladder method for different standard candles. And so I think like my initial argument that the culprit was definitely the lambda CDM model, or in order to resolve the tension, the Hubble tension, we need to look into new physics or possible new physics. Now it's less robust or less solid, if you wish. But then I, started thinking about something different. Like, okay, so if the problem cannot be said to be definitely in the lambda CDM model, I'm not saying that it's not. I'm just saying that with these premises, we cannot conclude that the problem is in the lambda CDM model. Then maybe the problem is that we need more systematics, which was basically the other possibility. And so here's another possibility. Here's another thinking, another reasoning. So let's distinguish 3 types of robustness analysis. They're called direct replication, methodology replication, systematic replication, and conceptual replication. They're actually 4, not 3. And this was a distinction made by Fletcher and Swan, and a distinction that was recently used by Merrick Wedwin to also discuss robustness in the Hubble tension. So what I want to focus on right now is systematic replication, which is the idea of reproducing the same study by changing a single variable to find out causal powers. So the idea is, well, let's look at different standard candles, right? We have TRGBs and Cepheids. So they're basically maximally overlapping in the sense that they're just a change of standard candles within the distance ladder method. So we know that basically systematic replication in that case fails because they don't give rise to the same value. And so maybe if we look into, if we run robustness analysis more deeply against these 2 different standard candles, then maybe we find out that new systematics are needed, or new data are needed, or that statistical hour data analysis is not good enough or accurate enough to just account for this discrepancy. So the idea is, well, we run systematic replication, which is like a reproduction of the study. It amounts to reproducing the study by changing one single variable, and our two variables right now are the standard candles, TRGBs and Cepheids. Here's the problem. Are they really one variable difference? So can we really consider Cepheids and TRGBs as just one variable difference in the way we calculate H0 within the distance ladder method? I don't think so. So let us look at the advantages and disadvantages of using different standard candles in the distance ladder method to calculate H0. So TRGBs, for example, we know their physical mechanism. Basically, the core helium flash, it's well known and understood physically. Then they're present in halos of galaxies where crowding and blending are minimal, so that limits systematic errors. They're present in halos of galaxies where the effects of dust are minimal, and then their metallicity relates directly to the observed color. There are some disadvantages, for example, the fact that there might be some false positives because peaks of comparable strength can impact the measurement of the true tip. And then here I quote, target field placement is critical. This is from Friedman, 2024. Too close and crowding, blending, reddening become issues, and too far out and the number density of stars is too low for precise measurement of the tip. What about JGBs? Well, for the most, the advantages are, for example, the fact that they have the dominant population of the reddest stars in galaxies. They are very bright and so easier to detect in a sense, and they're fairly common in galaxies with intermediate age population stars. The disadvantages, well, for the most part, is that they are fairly new. They're a fairly new method, and that means that basically new systematics or errors or factors that we haven't accounted for might be lurking around and we just don't know about them. What about Cepheids? Well, the advantages, the main advantage is that basically the relation between period, luminosity, and color is well defined and makes them high precision standardized candles. They are among the brightest stars indicators. They are relatively new stars, and then they can be found in abundance. And they're fairly straightforward to discover also because of their period luminosity relation. Some disadvantages are the fact that, for example, they're located close to regions of gas and dust where they are created, and so they need precise corrections. And those corrections usually involve processes that involve risk of biases, such as noise threshold for inclusion, corrections for crowding, blending, and corrections for metallicity. So this was just to see how basically I think Cepheids, TRGB stars, and JRGB stars, they're not just one variable in the distance ladder method. They're indeed like different standard candles, and they come with very different problems and different advantages and different disadvantages. So they're different in their evolutionary stage, mass range, energy source, luminosity, periodicity, and metallicity, for example. And all these factors need to be accounted for when we use them to calculate H0. And so it's really not right to say that basically they're just one variable difference, I think. And if they're not just one variable difference, it means that we cannot run robustness analysis just based on systematic replication, but we need a better form of robustness analysis, or at least a deeper one. Or at least we cannot conclude that it's just a matter of systematics for why TRGBs, for example, and Cepheids give rise to different values with respect to H0. And so therefore, this is the conclusion. If you want robustness, you need better robustness. What does that mean? Well, we've seen how basically running robustness analysis, trying to argue that lambda CDM model was the culprit of the H0 tension is, in a sense, a failure, or at least not conclusive, because we don't have enough good reasons to say, sure, the distance ladder method is robust enough that allows us to say lambda CDM for sure is the problem. But then, if we run the opposite argument, or kind of the opposite argument, where we say, well, then it's definitely a matter of systematics, because if we just look at different standard candles, then we can conclude for sure that new data are needed. Well, it's not exactly like that either, because that's enough to say that's not enough of a definition to use robustness analysis in a general way to actually conclude that it's definitely new systematic. We need that, therefore, if you want to run any of such arguments, we need first a better robustness analysis. And so now I'm going to try to say, like in the last like 2 minutes, I'm going to try to show you how this new definition of robustness analysis that we need also comes with a lot of work. Why? Well, first of all, because I think we would need a bottom-up approach for which basically we have robustness analysis of individual standard candles with different calibrations. For example, we need robustness analysis that evaluates variation of metallicity, tests variation of the Leavitt law, different samplings for TRGBs, and so on and so forth. So within each standard candle, we run robustness analysis for how that standard candle is used to calculate H0. But then we need robustness analysis for different standard candles, like a comparison between different standard candles in the context of the distance ladder method. And only then we can move to methods that are independent from the lambda CDM model. And then, only then, we can actually try to say something more meaningful about whether the Hubble tension can be resolved by at least considerations with respect to robustness analysis, because then we can run robustness analysis between lambda CDM model and autonomous methods. Just to give you an idea of what this implies, we have different model-independent methods. For example, we have quasar lensing, we have different measures, we have the infer H0 from observed time delay and less mass models. So different lens mass models give rise to different results, as you can see from the slide. We're like basically by using different lenses, we obtain fairly different results. But then we have, for example, mega masers, which also provides fairly different results based on the distance, the object that we're measuring the distance from. Then we have, for example, gravitational waves that have been used to calculate H0. For example, with LIGO and Virgo, we obtain basically gravitational wave and electromagnetic signals from the merger of binary neutron star system that calculated H0 to be 74 kilometers per second per parsec. Then we have improved measures that calculated estimated H0 to be 70, and then even better measurement that estimated H0 to be 68. Notice how we went from basically the high level to the low level with using the same method, gravitational waves. Then we have faster radio bars, which give fairly different results based on how many pulse pulses we consider. There is one thing to be considered here that I did not mention at first, but it's important. Please notice that in the model-dependent methods, the errors are quite significant. And so it is also possible that a robustness analysis of such methods might not be as conclusive, precisely because the errors are quite significant. For example, in the original measurement of gravitational waves, in the original detection of gravitational waves, H0 was calculated to be 74 with an error of plus 16 minus 8, which is significant. So that's why basically I think if we want to do this whole project of using robustness analysis to investigate H0 tension, we need to start from distance ladder methods and methods that actually provide measurements with lower mistakes, lower errors, sorry, not mistakes. For example, we can look at the distance ladder and the different measures for the distance ladder, where we have basically different methods within the same distance ladder method, because we have Mira calibrators, we use two efficient relations, we just use TRGB calibrations or different TRGB calibrations, we use TRGB plus Cepheids or just Cepheids alone. And so each of these, I think, methods need to be kind of evaluated in terms of robustness before we can say anything about robustness with respect to a higher layer, which is, for example, distance ladder method compared to the lambda CDM model based methods. And so the idea is that that's a lot of work. It doesn't mean that it shouldn't be done. It just means that we need to start small, and I conclude here. We need to start basically from a bottom-up definition of robustness analysis, and that's because, well, if we evaluate the Hubble tension with the general definition of robustness analysis that I presented here, For example, we can say that the culprit is lambda CDM, but the argument is not conclusive. At the same time, if we say that the culprit is mu systematics, well, that's not conclusive either. And so, as I was saying, we need a bottom-up definition of robustness analysis, perhaps borrowing some knowledge from the computer science field, where they have like a much more precise definition of robustness analysis, perhaps too narrow though, but that's just my opinion. And then we need a bottom-up approach. We need a bottom-up robustness analysis of the distance ladder, and then we need a bottom-up approach of the lambda CDM based methods, and only then we can compare. That's it. Thank you.